initially, let's see why do we need to discuss about characterization of any cementitious material. Can I have your views on this? If we would like to, if anyone would like to share their views, why do we need to characterize anything? We all know that concrete is a heterogeneous material. Heterogeneous here, I mean like we have different types of materials that go into making a concrete, and we would like to have concrete as a homogeneous material towards the end. So we expect concrete to behave as a homogeneous material, but the composition of different materials that are going into concrete is heterogeneous in nature. So each material that goes into making this concrete is of different type, right? Like we can have a binder, we can have an inert material, we can have chemical admixtures that are going into it, we can have different types of mineral admixtures that are going into it, and we also use different types of specialty admixtures to make our concrete suitable to serve for different severe conditions. So all these materials inside this concrete, which we see outside to be a fantastic material and to be is standing strong for some time, we we should understand really like what is the microstructure of this material made of. How dense is that microstructure? Because all the macrostructural properties that we talk, either in terms of durability or in terms of mechanical properties such as compressive strength and anything, that is dependent on what is happening at a microstructural level. So we would like to understand how dense is the microstructure and what is this microstructure made of. Is it only different types of materials that were put together, or are they bound together? If they are bound together, with what type of binding material are they bound? What is the porosity of that particular microstructure? How stable is the formed microstructure? And what are different factors that influence the stability of this? Say, if it is stable in one environment, will it be stable in another environment as well? So we have all these different questions in mind. Although we see that microstructural at a microscopic level, the concrete is behaving really well. What is contributing to the microscopic behavior is what is happening at a microstructural level. Now, how do we understand that? To see how a system is working at a microstructural level, we need to have different techniques. We have several analytical techniques such as TGA, X-ray diffraction, NMR, calorimetry, MIP, IR spectroscopy, microscopy, and again in microscopy we have different levels, and we also have EAS, and there are several techniques as the science is progressing, the techniques are evolving. As the techniques are evolving, we are able to understand the material in a better way. So these things are going hand in hand with us. In this lecture, however, we'll see about few of these analytical techniques which are helpful in understanding the material in a better way. First, we'll start with thermogravimetric analysis. Thermogravimetric analysis is part of a thermal analysis. Now, what is this thermal analysis? This thermal analysis is an umbrella in which thermogravimetric analysis is one part of thermal analysis. If we see, it is a general term which covers variety of techniques that can record both physical and chemical changes in a substance as a function of temperature. Physical and chemical changes means like if I take some material and if I expose it to different temperatures, what is happening to that material? The material can undergo a physical change. The material can also undergo a chemical change. Now, what do we mean by physical change that a material can undergo? Physical change here we mean like what is happening? Is it melting, or is it crystallizing with temperature, with the provided temperature, or is it expanding in volume, or is it shrinking in volume? All these things can be attributed to physical change. Now coming to chemical change, what is happening within the material? Is the material stable, or is there any decomposition that is happening in terms of either decarbonation or dehydration or several other ways like oxidation and several other ways that material can undergo a chemical change. Construction materials can also undergo both physical and chemical changes upon heating, and hence thermal analysis can be used to understand or investigate the microstructure of construction materials. There are several techniques like thermogravimetric analysis. In thermogravimetric analysis, we see what is the change in weight of the substance with change in temperature. And while there is a change in weight, means there is some chemical change or physical change that is happening within the system. Let us assume that if there is a chemical change, means there is either decarbonation or dehydration or decomposition of the system. Now, like in that particular temperature, whether dehydration is happening or decarbonation is happening, that we don't know from only thermogravimetric analysis. Because in thermogravimetry, we measure only what is the change in weight with respect to temperature. Why is that change happening? Is it because of loss of water or is it because of loss of CO2? That we are not aware of. To understand that, now we'll see what are the flow gases that are evolved from these materials, and we'll analyze that gas. That we do using evolved gas analysis. So these two are these days clubbed together, and we have a technique called TGA MS technique. MS there refers to mass spectroscope. There we understand what is the evolved gas that is coming at different temperatures when the system is exposed to different temperatures. We also have differential thermal analysis and scanning calorimetry. These are one and the same. We'll see in the next slide. We also have thermomechanical analysis. In thermomechanical analysis, we'll understand what is the change in deformation, like mechanical changes that is happening within the system, whether it is expansion or whether it is any other mechanical changes that can happen within the system. In dynamic mechanical analysis, we'll understand what is the change in like phase changes like blast transition temperature, or what is the change in moduli of the system. These things we can understand through dynamic mechanical analysis. There is another technique called dilatometry. In dilatometry, we can understand what is the change in volume. Now, if we see differential thermal analysis, in differential thermal analysis, we have this like now we understood that we have some sample that we are providing temperature to that sample, and then we are understanding what is happening to that sample upon application of heat, whether the sample is taking the heat to undergo some reaction or whether the sample is releasing more heat, right? So this is what we understood till now. This we can also see, like even if without giving the heat, we can also understand what is happening at a constant temperature. That we'll see in calorimetry. Okay. In differential thermal analysis, we have a sample system, and to avoid the noise that we get from the surrounding, we always have a reference system. In the sample here, both sample and the reference were provided with a single heat source, means both sample and reference were kept in a same environment. Same environment here we mean either we are heating it at a same rate or we are cooling it at a same rate. When we do that, what is the difference in temperature of the sample and what is the difference with respect to temperature of the reference is what we monitor over here. So we take temperature of sample and temperature of reference when this entire system has been kept at a constant heating rate or constant cooling rate. So what happens over here, if it is an heating rate, means the sample can undergo some again physiochemical changes that can either like result in an enthalpy change within the system, that can either evolve heat or absorb heat. When that is happening, there will be a temperature difference we can measure between the sample and reference. So the plot would be the difference of this temperature that we measure as a function of temperature with which we are heating both sample and reference. This is called a DTA curve. We'll get endothermic transitions if the sample is taking the heat and then undergoing some reaction, then there would be endothermic transition over there. Then we also have differential scanning calorimetry, where it is a technique which can record the energy that is required. Here what we are measuring the temperature difference. Here we don't require the temperature difference. We would like to have the temperature difference to be 0. In this case, we may need to provide external energy. Either if the sample is taking the heat, then we may need to provide external energy to yield the temperature difference to be 0. So over here, we measure how much amount of heat we are providing to the sample for the temperature difference to be 0 with respect to reference. So towards the end, these two would provide us same information, what is happening within the material when they are exposed to different temperatures. The plot in DSC is function of heat applied or heat given to the system as a function of temperature. Temperature is in your x-axis. Now coming to TGA. TGA measures what would be the change in weight of the sample when it is exposed to different temperatures with respect to a scan. So here what we do, this is an example that we are providing. We have taken commercial calcium hydroxide. Calcium hydroxide, why we are preferring calcium hydroxide over here is like this is an unique sample where it will have a loss of weight at a particular temperature region. So if you see, this is TGA curve where till 400 degrees centigrade, the weight loss within the sample is almost negligible. But after 400, you can see a significant drop in the weight loss of the sample. And also there is a minor weight loss that we can observe till 600 degrees centigrade. Now, why is this happening? So if you take calcium hydroxide is Ca. Okay, so calcium hydroxide is CaOH twice. CaOH twice when we try to heat it at different temperatures, and when it reaches a temperature of 400 to 500 degrees centigrade, the OH twice or the structurally bound water from the calcium hydroxide will decompose or will dehydrate, and then we'll be left with free light. This calcium hydroxide upon atmospheric conditions, it can also carbonate to certain extent. That carbonation can be seen over here with the weight loss that we can see in the region between 500 to 600 degrees centigrade. So this is the place where loss of CO2 is happening upon heating, and this is the place where loss of water is happening upon heating. If we take ordinary Portland cement curve, in OPC, we can see that there are several weight losses, right, in the same temperature scan. Both are exposed to similar some temperature scan. In calcium hydroxide, we can see there is a single weight loss predominant at a single temperature region, but that is not the case with ordinary Portland cement. In OPC, we can see that there is a slight weight loss that has started even initially, like over here from 70 degrees itself, the weight loss has started, and then there is a significant drop, a slight significant drop. Then again, we have a significant drop over here, and again, we have a significant drop over here. This is our OPC curve. Now, we'll not be knowing whether there are several different systems that are undergoing a temperature mass change or weight change in this particular region or not. To understand or to identify several or consecutive weight losses that can happen within the system at a particular temperature region, we can always do a first differential of this particular TGA curve. When we do first differential, we'll have this blue curve. Blue curve is the differential thermogravimetric curve that we got. Here we can clearly see that, although we may not be able to identify, we may see that there is a continuous weight loss over here. But at what point it is predominant is not able to, like we cannot able to identify over there. But from TGA, we can see the main peak is somewhere near to 70 degrees over here. Then somewhere near to 100, we have another peak. Then near to 420 or 450, we have another peak. And somewhere near to 650, we have another peak. Now these peaks corresponds to different types of hydration products which are decomposing at those temperature regions. If we see the thermal reactions which can undergo weight change, mainly related to our OPC systems, we have either dehydration of system or any hydration products that we have that can be dehydrated, which will result in loss of water. And because of loss of water, we can see a change in your mass. We can also have dehydroxylation. Dehydroxylation will come from loss of structurally bound water. So we have seen in earlier slide that calcium hydroxide can dehydroxylate and provide us calcium oxide and loss of water over there. Decarbonation can happen where there is loss of CO2 and that would result in mass change. There can also be oxidation of system. The oxidation of system can induce an increase in mass rather than a reduction in mass. We can also have decomposition. Decomposition in general over here refers to loss of water itself. Any product where the loss of water is happening, we can say that decomposition is happening. We can also have phase transition or melting. This is mostly towards crystalline materials, which may undergo these physical changes upon heating or at different temperatures. Along with the weight loss, as discussed earlier, we can also understand what type of gas it is evolving at different temperature regions. So over here, if we see TG of fly ash, we can see that there is almost not much weight loss, and then but at this temperature region we can have significant weight loss, and then again a weight loss, and then slight weight gain over here. That is what we can see in this temperature scan. If we see what are different types of gas evolved across these temperatures, if we see this black curve says at what all temperatures there is loss of water. So here we can see initially there is loss of water from the free water that is present in the system. And then there is this loss of water in 400 region, which is due to loss of hydroxyl ions or loss of bound water from some of the bound products. And then we also have, and then we'll not be seeing any water loss at any point of time beyond this one. That is what this curve says to us. If we see this dark gray one tells us at what temperature regions there is loss of CO2. And light gray one tells us at what temperature regions we have loss of carbon monoxide. This is the case for fly ash. If we see the same TGA curve for GGBFS, in GGBFS initially we have loss of water and can also be seen through this evolved gas analysis. And continuously there is evolution of some hydrogen sulfide. And if we don't provide sufficient reduction or reducing environment, this hydrogen sulfide can oxidize, and that can result in increase in your weight loss of GGBFS after certain temperature. We can also see there is evolution of CO2, and there is also evolution of SO2 towards the end regions of your temperature zone. This is one of several other TGA equipments that we can see. This is STA 8000 from Perkinel Mermaid. This is the furnace in which we will keep our sample, and we will increase the temperature of the sample by increasing the temperature of furnace. So if we see in a finer fashion, we have crucibles over here. We have a weighing balance. On a weighing balance, we'll be having two crucibles. One crucible will hold your sample, and another crucible is for the reference. And both the sample and reference will be heated at a similar heating rate by providing some thermocouples over here. Thermocouples will govern at what rate the temperature is increased within the sample. So we'll have furnace temperature separately and the sample temperature separately. And since this is happening on the balance itself, the balance will keep on measuring what is the change in mass of your sample that is happening at different temperatures over the temperature scan that we provide to the system. So since this is an equipment based, there are several factors that governs what is the TGA curve that we are obtaining towards the end. We'll see what are different factors that govern this. There are several influencing factors like type of measuring device we are using, what kind of vessel we are using. Vessel over here, I mean the crucible that we are using for holding either the sample or reference, whether it is closed lid or whether it is an open crucible. We can also, like the heating rate will also govern the decomposition temperatures. The amount of solid that is present will also govern this. The particle size, type of purging gas flow rate, and pre-treatment of sample. We shall see how most of these influencing factors affect the TGA curve of our cementitious systems. If we see the heating rate, this is one example. So what is happening? We have one sample, crucible, and then we are keeping one sample over here. And then we are heating it. When we are heating it, there is some chemical reaction and physical reaction that is happening within the system, due to which there is change in mass of this sample. And that change in mass is continuously measured with respect to temperature. That is what we are doing in TGA. It seems so simple at this point of time, but to measure this small change in mass that is happening within the sample at different temperatures, the equipment that I have shown earlier would cost somewhere near to 40 to 45 lakhs. So that's how sophisticated equipments are so costly to understand. So over here, what we see is if we heat this at a higher heating rate, what happens? There will be some loss of water. This loss of water would occupy this space that is available above the sample. So now this space will have lot amount of water vapor because of dehydration of this sample at earlier temperature. Now, if we keep on increasing the temperature, there might be another hydration product which would try to dehydrate. Now, for dehydration to happen, that water vapor molecules should able to accommodate in this particular region, which is already occupied by certain amount of water vapor. So, in this case, the actual decomposition temperature would shift to higher temperatures because of the accumulation of water vapor that would suppress the decomposition which would have happened at earlier temperatures if this was not there. So what we do for this, now we will try to eliminate this water vapor continuously, or whatever volatiles that we are getting above the sample continuously. So to eliminate that, we will keep on purging this system with a purge gas. Now the question is that purge gas should not react with the sample now. So we ideally pick up any inert gas as a purge gas, which should keep on eliminating the volatiles that are accumulating above the sample, which is due to either dehydration or decarbonation or any other decomposition that can happen. And that should not also react with the sample. So we pick up an inert gas, either nitrogen or argon, as a purge gas. Now the rate at which we are purging will also affect, like similar to the rate at which we are heating. If we see over here, this accumulation will also depend on what type of vessel we are using, right? If it is a closed vessel means we have a lid on the top of this crucible. If we have lid, we are not allowing these volatile gases to escape from this environment. Means we are accumulating more amount of water vapor over here. Means that would shift your decomposition temperatures to even higher temperatures. That is what is happening over here. So if I compare between 20 degrees centigrade per minute heating rate between an open vessel and the closed vessel, in open vessel the decomposition temperature of gypsum is somewhere near to 140 or here. But in a closed vessel, it has been shifted even beyond 140. And we can also see that the peaks are here are like we have two peaks that are near to each other, but these peaks can be distinctly distincted over here when we use the closed vessel system. So here what is happening is you have a gypsum. Gypsum is calcium sulfate 2H2O. 2H2O. That 2H2O, now gypsum is dehydrating to hemihydrate. Hemihydrate is 0.5 H2O. Means 1.5 moles of water has been lost in this weight loss that we are seeing. And now we have another system with 0.5 H2O. That 0.5 H2O has been lost at even higher temperatures. So now gypsum, upon dehydrating, it has converted to hemihydrate, and now hemihydrate has dehydrated totally. That is what this gray dotted line tell to us. If we see the same system, like if I compare the open vessel with lower temperature, lower heating rate, here we can see at lower heating rate, the rate at which the water vapor accumulates over here would be lower. So your decomposition temperatures would be on a lower side. Anyone has any doubts in this? Okay. We have discussed about the gas flow rate. Gas flow rate will also tell us at what rate we are removing the volatiles that are accumulating on above the sample. And we have also seen what is the type of purging gas. If we see over here, this is a TGA curve for commercial GGBFS. The dark gray color over here shows the TGA curve for at 100 ml per minute flow rate. 100 ml per minute flow rate means we are removing the volatiles at a higher rate. So there is no point of accumulation, and hence there is a continuous weight loss. Over here, if we see for 20 ml per minute, after some time, the reducing environment that the nitrogen is providing to that system is not sufficient enough to suppress the oxidation reactions that GGBFS can undergo. In the previous slides, we have seen that GGBFS has evolution of H2S. This H2S will now react and form an oxidized product that would increase the weight over here. So that we can see clearly that there is an increase in weight loss. So there is an increase in weight, not a weight loss. Whereas if we increase the flow rate of the purging gas, then we can have a continuous weight loss of the system. If we do the same thing in air the material, there is no oxidation, there is no reducing environment that we are providing now. So the material is free to oxidize, because of which we can see an increase in weight after certain temperature. If we is there something? Is anyone talking? Sorry. Okay. If we see what is the effect of amount and size of solids, everything will pin down to this water vapor accumulation that we have talked, or volatile gases accumulation above the sample that we have seen. If we have higher amount of sample, then it says that there will be higher amount of accumulation of water vapor. That would push your decomposition temperatures to higher temperature regions. So this is the same sample, but if we keep only 0.5 milligram, the decomposition is happening at a lower temperature. But if we increase the weight to 1 milligram to 3 and 10, we are seeing that the decomposition temperatures are pushing to higher temperatures. We can also see that with higher weight, we are not getting a well narrow defined peaks. Okay. The same is the case with size of the solid. If you have higher solids size, that would also affect the decomposition temperatures. And pre-treatment of sample will also affect the decomposition temperatures that we are seeing. Pre-treatment here we mean the hydration stoppage method that we have adopted to remove the free water from the sample. If we do that, we can stop the sample at a particular hydration age. Then we can start analyzing what different types of hydration products are formed, how much amount of each hydration product has formed, and various other things that we can analyze at that particular hydration age. If we see, there are different types of hydration stoppage techniques, like solvent exchange method. In solvent exchange method, we take the sample, we'll try to remove the free water that is present in the sample by dipping it in alcohol. Alcohol here we take isopropanol. Isopropanol now will replace the free water that is present in the sample. So we'll end up having a sample with isopropanol. Now that isopropanol should also be replaced by something else. So we take now diethyl ether as a second replacing solvent. So if we now submerge the IPA replaced sample in diethyl ether, then we can replace the entire IPA with diethyl ether, and diethyl ether is highly volatile. So through this process, we can remove the entire free water that is present in the sample. That is what the solvent exchange method talks about. And we have vacuum desiccation that we can do. So vacuum drying we can do. So here you can have your sample in a desiccator that is applied under low vacuum, and you can also add some amount of dry ice. So this will keep on removing the free water that is present within the sample. You can also do freeze drying. In freeze drying, we'll try to bring down the temperature of the sample initially by submerging it in liquid nitrogen. Now it has been, the free water that is present in the sample has been sublimated in the form of ice. Now we will expose that one to higher vacuum levels. Now directly there is a sublimation of this ice. The ice form will directly convert to gas over there. So we are directly removing the free water by first converting it into ice, and from ice to gas. So that is what the freeze drying technique works on. And this is an oven drying technique. In oven drying, we keep our sample at somewhere near to 100 degrees centigrade or 70 degrees centigrade in an air oven or an open oven. And then we'll try to remove the water from that free water that is available in the system. Now they tried to study what is the effect of different hydration stoppage techniques on the hydration products that we are trying to understand. It doesn't mean that all these samples are different samples. These are all same sample. For example, if you talk or if you understand, if it is OPC 28-day sample, let us consider that. The OPC at 28-day sample has been taken and has been exposed to different types of hydration stoppage techniques. And then they understood what is the THA curve that they can obtain when they expose the sample to different temperature scan. But what is interesting over here is, although the sample is one, means ideally we should be able to get same hydration curve or same TGA curve or same weight loss curve. But depending on the hydration stoppage technique, the weight loss curve has been changed significantly over here. That is what we can see, right? Like for some weight loss, like solvent exchange, we have higher weight loss in this temperature region between 100 and 200. And there is also weight loss that we can see. And there is small weight loss that is obtaining near to 600 to 700 over here. But that is not obtained in, or that is not seen visibly in either oven drying or vacuum drying one. So if we see what is the different types of products that are formed or that are available after this hydration stoppage techniques, we can observe over here that is given in this slide, where we can see that if it is solvent exchange technique, we can preserve ettringite in the sample. And the ettringite decomposition will happen before 100 degrees centigrade. That's why we can see a lot of weight loss that is still preserved in the sample. This is not the free water that is available, but this is the ettringite that has been saved. Saved, I mean, like if it is oven drying, we are directly exposing the sample to 100 degrees centigrade. But ettringite will try to dehydrate the moment the temperature reaches to 70 degrees centigrade. Means by the time that we are trying to remove the free water just to stop the hydration, we are also decomposing one of its hydration products. Means will not be able to see what type of hydration product is formed or how much of that particular hydration product is formed through this TGA technique. So it is very important for us to if we are trying to match different samples in your laboratory, it is important for us to maintain same type of hydration stoppage technique across these samples if we are trying to investigate between the samples or compare between the samples. It's not only the hydration stoppage technique. Once we stop the hydration, after how much time are we doing TGA? And what is happening in the storage duration? During the storage duration, the carbonation can happen within the sample. Here, this is one such example where there is they have done the TGA after 3 days, after 7 days, and after 31 days. And they can see that the weight loss that is corresponding to initial one has decreased when they have performed the sample or TGA after 31 days. And this reduction in weight loss over here has been seen as increase in weight loss in this particular temperature zone. Means some amount of products that are available over here have been carbonated, and that carbonated product is decomposing in this particular temperature zone. So the carbonation during storage is also an important thing that we have to eye upon, and we need to store our samples. We either need to perform the experiment as immediately as possible, and if that is not possible, we have to store our samples in a desiccator with proper decarbonatant with that we can add either soda lime or any other material which can carbonate earlier before your material can carbonate, or you can always store in a desiccator. You can purge some amount of N2 and apply vacuum over there. Now we shall see at what different temperature regions, different types of hydration products that are commonly available in ordinary Portland cement systems would decompose or dehydrate. If we see gypsum is added to the clinker to make OPC. Now, if we see gypsum as such, gypsum has two different temperature regions in which it can decompose. In initial one, which is from 100 to 140 degrees centigrade, the gypsum will dehydrate and change to hemihydrate. And the second weight loss step that we can see is from between 140 to 150 degrees centigrade, where the hemihydrate will now further lose the remaining 0.5 moles of water that is present and becomes anhydrate. Portlandite is it is both the best material that we would like to have, and it is the material that we would not like to have in the system as well because of durability issues. But we would also like to have Portlandite within the system to maintain the alkalinity of the system. So, that's why this is one of the main products that we talk and we usually talk upon. If we see Portlandite is calcium hydroxide. Calcium hydroxide will have a decomposition temperature or dehydration temperature at 460 degrees centigrade. And at that one, we can see a dehydroxylation that can happen. So we have calcium hydroxide that can dehydroxylate to calcium oxide, and there is loss of water that we can see. And this will result in loss of your mass. If we see the molecular weight of calcium hydroxide is 74, calcium oxide is 56, and we can have loss of 18 grams. So if we actually take 74 grams of calcium hydroxide, do TGA, we would end up having a mass of 56 grams now, and the total weight loss would be somewhere near to 18 grams. That is what we are understanding from this. We can also have another type of hydration product, which is magnesium hydroxide. This is not so usual in our systems, but magnesium hydroxide is also present in few of cementitious materials. In magnesium hydroxide, would dehydroxylate in the temperature region of 420 degrees centigrade to magnesium oxide and water. There is again loss of water over here that would result in weight loss. We have magnesite, which is MgCO3. Between temperatures 500 to 600 degrees centigrade, there would be mass loss that is observed due to decarbonation of magnesite. Again, we'll have periclase, magnesium oxide is periclase, and then we have loss of CO2 from this system. We have calcite. Calcite is calcium carbonate. Calcium carbonate is usually seen in 6 different polymers. But if we see in cementitious systems or carbonation of cementitious systems, we can see in 3 different polymers like calcite, waterite, and aragonite. Among all these 3, calcite is most stable, and the decarbonation of calcite will happen in the temperature region between 600 to 800 degrees centigrade. And then there is loss of CO2 that you can see when we expose CaCO3 to a different temperature scan. The main hydration product, which is calcium silicate hydrate. Unfortunately, calcium silicate hydrate has no specific or narrow temperature region in which it can show us a weight loss or dehydration, because calcium silicate hydrate has different types of water that is available within its structure. Like we can have either interlayer water, we can have gel water, and we can have adsorbed water in CSH. So all these different types of water would dehydrate at different temperature regions. If it is free water, it can dehydrate even at lower temperature regions. If it is bound water, it will take even higher temperature for it to dehydrate, because of which we can see a continuous weight loss of CSH between temperature regions of 550 to 600 degrees centigrade. Over here, we can see loss of water present in different interlayers and dehydroxylation. And around 800, we can see dehydroxylation decomposition of CSH to wollastonate. Ettringite is another product which is formed. Ettringite is formed when C3A reacts with gypsum that is added to the system, and that would result in several types of AFT products, and the major AFT product that forms is ettringite. In ettringite, we have 32 moles of water. This 32 moles of water is held in columns of ettringite that is available. Since they are adsorbed on the columns, it is easy to dehydrate. So even at 100 degrees centigrade, you can see a loss of water that can happen, which is bound in the columns of ettringite. And around 200 to 400 degrees centigrade, like once this water is lost, now you'll have dehydroxylation of remaining water, and that would result in gypsite. You can also have thomsite. Thomsite is formed when you have both carbonation that is happening in the system. So you'll have calcium silicate, calcium carbonate, calcium sulfate, hydroxide with 15 moles. Or here at around 130 degrees centigrade, again, the water that is held in the columns is easier to remove. So those would remove at lower temperatures. And near to 400 degrees centigrade, there is loss of water from the hydrated systems and hydrated silica. And around 600 to 750 degrees centigrade, the CO2 that is present over here would loss. That would be decarbonation. We also have monocarbonate. Monocarbonate is formed when you have particularly LC3 systems. In those systems, we have calcium aluminate carbonate system, where in 60 to 200 degrees centigrade temperature zone, you can have 5 moles of water lost. And from 200 to 300 degrees centigrade, the remaining 6 moles will be lost. And at around 650 degrees centigrade, there will be loss of CO2. So monocarbonate will also have steps of temperature loss at different temperature regions. We have monosulfate. Monosulfate is formed when ettringite would react with C3A, and when the gypsum availability is not there, or after the gypsum depletion, and that would result in an AFM phase, which is monosulfate. monosulfate, there will be loss of water from 60 to 200 degrees centigrade from the columns of it. And entering, around 250 to 350 degrees centigrade, there will be loss of 6 moles of water from the octahedral layer. You can also have Friedel salts. Friedel salts are formed when there is an ingress of chlorides that are coming into your system. These chlorides would react with C3Fase, and some of the chlorides would be bound within the system in the form of a salt, and that salt is Friedel salt. So the formula is like you'll have calcium oxide, calcium chloride, and Al2O3 system, and you have 10 moles of water over here. So at lower temperature regions, you'll have loss of interlayer water, and from 250 to 400 degrees centigrade, you'll have loss of water from the main layer. Stratlingite is not so common in OPC systems, but if you have OPC plus fly ash system where you have higher amount of aluminates, then you can see a formation of another hydration product, which is stratlingite. This stratlingite also has 8 moles of water, and those will be lost when the temperature is somewhere near to 200 degrees centigrade. Hydrotalcite is formed when you have a significant amount of magnesium oxide that is present in the system, and this is one of the hydration products that you can see in alkali activated materials, which are alternative cementitious materials. The decomposition of hydrotalcite is as follows. Up to 270 degrees centigrade, there will be loss of 4 moles of water, and around 400 degrees centigrade, there will be loss of the other 6 moles of water from hydrotalcite. So we understood that from thermogravimetric analysis, we can see at what different temperatures will have how much amount of weight loss, and what is that weight loss correspond to. Is it due to loss of water, or is it due to loss of CO2? That is what we can understand. So depending on that, now we can back calculate how much amount of total water is held within the system during hydration, and that water we call as bond water. So if we know the total weight loss, and if we know what is the weight loss because of loss of CO2, the remaining weight loss is due to loss of water, and that water is coming from the hydrates. If there are no hydrates that are present, there will be unhydrated product. The unhydrated product will not dehydrate or decompose at this temperature regions that we have seen. Similarly, the weight loss that is corresponding to 400 to 500 degrees centigrade can also be considered to understand what is the amount of Portlandite present. Same is the case for carbonate. And we can also understand what is the reaction of Portland cement at different ages, like how much amount of reaction have happened in the system with respect to curing age can also be understood. We can also see what is the reactivity of supplementary cementitious materials. Say supplementary cementitious materials would work on pozzolanic reaction. Pozzolanic reaction means like you have precursor or a material which is rich in aluminosilicates. These aluminosilicates would react with calcium hydroxide. Now this calcium hydroxide is coming from reaction between ordinary Portland cement and water. Now this calcium hydroxide and the aluminosilicates will react and forms CSH. That is pozzolanic reaction. Means if we have supplementary cementitious material within the system, there is consumption of Portlandite. Now, how do we see whether the consumption of Portlandite have happened or not? That would be seen with reduction in the weight loss in that particular temperature zone. From that, we can understand what is the reactivity of supplementary cementitious material. Say how much amount of Portlandite has been consumed by 1 gram of supplementary cementitious material at different curing ages. We can also identify a few amount of X-ray amorphous phases such as CSH and Gibbsite through TGA. Now we'll see how to quantify the amount of material by considering the weight loss from the system. For that, I would like to I would like to open another platform. I'll just stop sharing now, and I'll start sharing my entire screen so that I can juggle between different screens or different windows. Anyone has any doubts till now?
There is a question in chat box.
My question is, sometimes the peak goes up and sometimes goes down. So is there any difference in it? I'm not so clear. Can you please explain what are you trying to say? Do we have anything from there?
No, ma'am.
Okay. Okay, then I'll go forward. I'll just open this file in Origin for us to understand how to quantify the amount of COH twice from the weight loss. So now we understood from TGA what we get is what is the weight at different temperatures. From the obtained weight and from the known initial weight, we can calculate what is the weight loss. And this is the curve that is saying what is the weight loss at different temperatures. Now from this, we can take what is the weight loss that is corresponding between these two. Can you see my cursor?
Yes, ma'am.
Okay, thank you. So we can see what is the weight loss that is happening in between these two temperatures. Since it is calcium hydroxide, we can directly take a tangent over here. Sorry, a straight line over here. I'll just remove all this first. We can take a straight line and we can also take a straight line and then see the difference in the y-intercepts between these two. That would tell us what is the total weight loss that had happened in this temperature zone that we are talking. So if I take initial y, it is 0.89 and the final one is 23.51. So the total weight loss is 23.51 minus 0.89, 22.62. 22.62 is your weight loss in this region. Weight loss is happening because of dehydroxylation of calcium hydroxide. So we have CaOH twice, that is decomposing to CaO plus H2O. Now we know how much amount of weight loss has happened. And we also know what is that weight loss correspond to. That weight loss is because of loss of water. So we can take this 22.62% as weight loss that is happening due to water. If we see the molecular weight, we have 74 over here and we have 56 and water is 18. Now instead of 18, we have 22 over here, 22.62. So if the loss of water is corresponding to 22.62%, how much amount of COH twice is present in this sample? That we can do a back calculation, which is 74 times 22.62 divided by 18. Means it is 92.99% of COH twice is there in this particular sample. This is commercial calcium hydroxide that we are talking. Means the purity of that sample is now around 93%. There is some amount of 7% which are impure. That we can see from this test. Now what is happening for the remaining 7%? If we see over here, we have also some weight loss that is present beyond 500 to 600 degrees centigrade. This is due to carbonation of calcium hydroxide. Now once calcium hydroxide carbonates, what type of product it forms? It forms calcium carbonate, calcite. This would decompose to calcium oxide and CO2. Now, how much amount of CaCO3 is there, or how much amount of this sample has been carbonated is the question. For that, what we do is, now if you see, there is a continuous weight loss over here. Means you can actually take a stepwise, then we'll see the tangent one. So you can take again a straight line over here and another straight line and see the difference in your weight y-intercepts. Here the y-intercept is 23.518. And it is 24.902. 24.902 minus 23.518, which is around 1.384. That is your weight loss corresponding to loss of CO2. If I come back to this calculation, the molecular weight of CaCO3 is 100, CaO is 56. And if it means like if you take 100 grams of CaCO3 and expose it to temperature region from 600 to 800, you'll have a mass loss of 44 grams because of CO2 decarbonation. Now instead of 44, how much we have? We have 1.38. If this is 1.384, how much amount of CaCO3 is present in the system? That we can back calculate again. 100 into 1.384 divided by 44 means you have around 3.145%. If I sum these two, this is around 93, this is around 3, means you have almost 96. Now we don't know what is the remaining 4%. That we have to understand again. Okay, this will tell us what is the purity of the sample that we are starting with. Now, if we see hydration of OPC, this is an OPC sample at 28 days. We have seen that there is a continuous weight loss that is happening till 400, and then there is a significant weight loss near 400 to 500, and again a weight loss near to 500 to 700 degrees centigrade. Now we have seen this, that the weight loss over here, initial one, is because of, like, if we see the DTG curve, although it is appearing as a smooth continuous one, we can see that there are two different humps. The first hump over here is corresponding to loss of water from attringate molecules. This is somewhere near to 72 degrees centigrade. This one. And the second one is near to 100 degrees centigrade, which is due to CSH, loss of water from CSH. And this is near to 450 degrees centigrade, which is due to dehydration of Portlandite. And this one near to 650 degrees centigrade, which is due to decarbonation of calcite. Now, if you see CSH, we understood that CSH will have a continuous weight loss. Now, if you would like to understand what is the amount of Portlandite that is present, we cannot directly go with taking a straight line and say taking the y-intercept directly, because that y-intercept now will have, like, if we see over here, there is a, if I take a straight line and another straight line before the start of weight loss and the end of weight loss, this weight loss will have a continuous weight loss that is coming from the previous temperatures, which is due to CSH. What I'm trying to say over here is, at every temperature, it is not a single phase that is dehydrating or decarbonating. There are several phases that are dehydrating and decarbonating simultaneously, which is resulting in the weight loss that we are observing. So each weight loss is not corresponding to dehydration of one particular phase. It is dehydration of several phases. Now we have to decouple it to understand what is the amount of Portlandite that is present. To do that, we'll adopt tangential method. In tangential method, we will, instead of taking a vertical straight line, we'll take a tangent. We'll take another tangent, and this tangent is because now CSH weight loss will not happen over here, like will not stop over here only. It will keep on continuing. So we'll take two slopes or two tangents like this, and now we will consider the straight line. We'll place this straight line in such a way that this is near to the DTG center that we have seen in the earlier slide. So this is your DTG. The peak center should match to your vertical. Now we'll keep like this, and now we will take, instead of, like in the earlier one, what we have done, we have taken a straight line and we have taken a straight line here. And then we have taken the weight difference between this intercept and this intercept. This weight difference will also include the weight loss because of not only Portlandite but also other products. To subtract that, now we are preferring tangential method. In tangential method, we are drawing one tangent and another tangent, and then we are placing a vertical line which is coinciding with the peak of DTG curve, and then we are considering this intercept as your y-intercept now. Now, if I take that intercept, that is somewhere near to minus 6.88, and this intercept is minus 8.29. So 8.29 minus 6.88, you have 1.41% of loss that is corresponding to dehydration of your calcium hydroxide. Is that clear? I hope I'm clear to everyone. The same method we will adopt to determine what is the amount of CaCO3. In CaCO3 also, you'll have a tangent that we place here, and we'll have another tangent that we place here. We'll take a vertical line, place in such a way that this area and this area are almost equal. Or you can always have your DTG curve and then keep the vertical line to the peak of the DTG curve at that particular point. And then take the y-intercepts. So from these two y-intercepts, now you can calculate the amount of calcium carbonate. We have seen in earlier one that how to calculate the amount of calcium carbonate from the weight loss and how to calculate the calcium hydroxide amount from the obtained weight loss. Here we are seeing how to refine the weight loss that we are obtaining and how to attribute that weight loss to loss of portlandate and loss of calcium carbonate. So loss of water from portlandate and loss of CO2 from calcium carbonate. Now, once we determine the portlandate content and CaCO3 content, sorry, CaCO3 content, what we can do now is, if we see this total TGA curve, this TGA curve is because of weight loss of decomposition of different hydration products that we are very clear now. Now, those different hydration products include either ettringite or CSH or portlandate or calcite. But calcite is not a hydration product. Calcite is conversion of hydration product because of atmosphere. Similarly, portlandate is not the thing that is contributing to the strength directly. Now, if we would like to understand what is the bound water or what is the water that is present in these hydrates, what we do is we consider the total weight loss that is obtained from the TGA curve, and then we'll remove the weight loss that is corresponding to CaCO3. If we remove that, we'll have weight loss now, which is purely due to weight loss of water. And that water is coming from hydration products. That particular product is called, or that particular weight loss is called bound water, or we can relate that weight loss to bound water. Not directly, but indirectly. Now that bound water can be correlated to compressive strength of your sample, which is measured at a macroscopic level. So higher is the bound water, that indicates you have higher amount of hydration products within the sample. Higher are the hydration products within the sample, higher is your compressive strength. Now, if we see TG of alkali activated materials, unlike we have several different types of hydration products or weight loss that we can see over here in OPC, in alkali activated material, we'll only see a one single weight loss almost or predominant weight loss in the initial regions, and later on we'll not see a significant weight loss. This predominant weight loss is due to the removal of water from CaSH. And there is a continuous weight loss, as we have seen. Even in CSH that is formed, you have a continuous weight loss. Or here also you have a continuous weight loss that you can see. Same is the case with this is with 100% of slag, alkali activated material, which is activated with sodium silicate of 1.5 molar modulus and 6 activated dosage. And this particular curve is with 50% of fly ash and 50% of GGPFS. We can see the amount of hydration products might have changed, but not the type of hydration products. That is what the initial understanding of this particular system, because we are not seeing any new weight loss at a different temperature. We are only seeing either a change in the total amount of weight loss at a particular temperature region. This is with addition of retarder. What we have seen over here is like with increase in retarder content, the total weight loss has increased. Ideally, what we see, the retarder would decrease the compressive strength. But what we got is the retarder, the addition of retarder has increased the compressive strength. Now, why is that happening? Then when we perform TGA, we understood that there is an increase in total weight loss that is happening with an increase in retarder content. This can also be seen over here, the total weight loss that is happening in this initial temperature zone, which is between 80 to 200 degrees centigrade, which is due to dehydration of CaSH. And in this region, you have decomposition of hydrotalcite. So you have predominantly CaSH and hydrotalcite as main hydration products in this particular system. And we can see with a change in retarder content is shown in this second numerical that we are talking. With a change in retarder content, we have not seen a new product that is forming, but we have seen change in the amount of hydration product that is forming. So we are in this lecture till on TGA, we have observed that there are several factors that affect the TGA measurements, and hence it is recommended to follow a particular protocol across all the samples in one laboratory. Say for cementitious systems, the general sample weight that is considered is around 20 milligram, because we have seen even if we change the sample size or the amount of sample, there is an effect on your decomposition temperatures. So at one day, if you are doing at 20 milligram, and if you take the 28-day queued sample, and if you have done the TGA on 10 milligram, then you'll have difference in the decomposition temperatures that we have observed. So to eliminate that, the best methodology that we can adopt is to maintain the constant sample weight. You can also use purge gas of nitrogen, and the flow rate you can maintain at 30 ml per minute if you are using OPC. But if you are considering slags, it is preferred to increase the flow rate near to 100 ml per minute to eliminate the weight gain that we see beyond certain temperature. The heating rate can be maintained at 10 degrees centigrade per minute, and it is always preferred to take the blanker. Blanker would eliminate the buoyancy effects that might come up into your system and the weight loss that we can see because of the flow rate of your gas. So it is preferred to take a blanker. Blanker here will keep the sample crucible empty, and will also keep your reference crucible, and then we will run the temperature scan. And the instrument related things can also be checked. We need to check for weight, temperature, and flow rate calibration at different durations. And it is preferred to use tangential method to quantify the amount of calcium hydroxide and calcium carbonate that is present in the system. And once these weight losses of water and weight loss of CO2 is determined, those weight loss we can subtract from the total weight loss to get the weight loss, to get the amount of bond water that is present in the system. Now we'll move forward to isothermal calorimetry. Before doing so, I would like to take up any questions if anyone has. Anyone has any questions? Yes, please.
Ma'am, my question is, there will be some unreacted particles during AM production. Will it
Yes.
affect any like interpretation of TGA curves?
If it is unreacted, means we are not having any unhydrated product. So you can always have even the raw material TGA, and then you deduce that raw material TGA from your hydrated material TGA to get what is the amount of hydration products. That is one way to look at it. If you are talking about AAM that is based on fly ash, or like the sample that can have different hydration, sorry, different losses. Unlike OPC,
Based on
OPC is
that, we,
highly crystalline. You'll have a straight line. If you do a raw material of OPC, you'll not see significant weight loss. But if you take, say, like coal fly ash, which has still some amount of unburnt carbon, in that case, even if you do TGA on raw material, you can see a weight loss. Now that weight loss should be accounted from your hydrated material TGA.
so from TGA only we can analyze uh, the product formation happened in AM, like in raw materials.
So
Like
all
we
these
can get the
analytical
compressive
techniques
strength
are,
in it.
yeah. So all these analytical techniques are like not one technique is sufficient. They all go hand in hand. So TGA will tell us what might have happened, but whether just say we are just attributing the weight loss from 400 to 500 now to Portlandate. Did we determine whether it is Portlandate? No. What we observed from TGA is there is a weight loss in this temperature zone. That temperature zone, it is because of Portlandate that we have understood through another technique. So all these analytical techniques should go hand in hand. That's why you'll not find any paper with only one technique. So they'll assume that, okay, this weight loss might be happened due to Portlandate. Now they'll see whether Portlandate is present in your XRD or not. Since Portlandate is present in the XRD, now this weight loss can be definitely attributed to Portlandate. So that's how they'll make conclusions and inferences from different analytical techniques. Anyone else have any? Yes, please. Do you have anything else? No. Thank you. Your good name?
I'm Abhilash from MIT Manipal. This is Conrad.
Okay, thank you.
Thank you, ma'am.
Ma'am, there are a few questions in the chat box, so we can just type.
What about weight loss with respect to calcium clay? Is there any specific range? Similarly for limestone. Limestone is basically calcium carbonate. So you'll be having a decarbonation of limestone that can be seen in different temperature regions, depending on what type of, again, carbonate is present in that. So there will be definitely a weight loss over there. And even in calcium clay is like, if at all, if you're talking about metakaolin, still you'll be having some amount of dehydroxylated systems. So those dehydroxylated water is always be visible as a weight loss at different temperature zones. So raw material, it's not like we have to do TG only on hydrated material. So always prefer to do TG on raw material and to eliminate those weight losses from your hydrated material to see what is the amount of actual hydration that had happened in the system. Anything else? I hope I have addressed your question, Vivek. How to identify nanomaterials interaction with the gel from PGA. So the gel that you are talking is CSH. Is that the case, Mr. Balaji? So what we can understand is if the nanomaterials are acting as a nucleation sites, because of which if there is an increase in hydration reaction, then your total weight loss of the system would increase. But where are these nanomaterials, whether they are adsorbed, whether they are not adsorbed, or how are they physically interacting cannot be seen with TG. TG will only tell us what is the weight loss at different temperature zones. If I have a blend of calcine clay and limestone, sorry, and what heating rate is recommended for geopolymer samples to avoid shifting decomposition peaks? So if you are making geopolymer, I believe that geopolymer that you're talking is also an alkali activated material. If that is based on slag, for raw slag, you have to do it 100 ml per minute. If you are maintaining 100 ml per minute for raw material, it is also preferred to perform other hydrated samples at different curing gauges at 100 ml per minute only, so that you can compare now. If I have a blend of calcine clay and limestone, is there any way to quantify kaolinite content availability? Okay, limestone will decompose again somewhere near to 600 to 800, but kaolinite will also like from kaolinite only will make calcine clay. So there is already some thermal decomposition that had happened in kaolinite, which has converted to calcine clay. So I'm not sure how to quantify now the remaining kaolinite which has not been converted to calcine clay. Are there anything else? Thank you. Thank you so much. So if there are no further questions, then we'll start the another topic, which is isothermal calorimetry. If everyone are fine with it, we'll proceed with that. So if we see isothermal calorimetry is the field where we understand what is the measurement of heat and heat production rate. 1 minute, sorry. It is a generic way for us to understand the processes. The processes that we are talking is either physical, chemical, or biological related processes, which are resulting in an enthalpy change. This is not a new technique. This is an old technique in 1740s itself. There are two scientists, which are Lavoisier and Laplace. They would like to understand what is the respiration rate of a guinea pig. So what they have done is they have kept this guinea pig on a big ice block, and they started to measure what is the amount of water collected at different durations and the rate at which, so towards the end, they'll have the total quantity of water collected and also the rate at which they have collected the water. From these two, they try to understand what is the respiration of guinea pig. But this is not a good system to understand, because once you are keeping guinea pig on an ice block, the relatively lower temperatures that are provided through the ice block would itself try to bring down the rate of respiration of guinea pig. So you are not actually measuring what is the respiration rate. And the second thing is like how accurately are you measuring the quantity of water. These two would govern to understand exactly what is the respiration rate of guinea pig. In cement field, we use calorimetry widely to study the kinetics and the extent of cement hydration. And it is the most common technique that we use day in, day out type. And we have several types of calorimetries. Among all those, we use isothermal calorimetry as a system through which we can understand the reaction kinetics of hydration. If you see types of calorimeters, we have three different types. Basically, we have adiabatic, semi-adiabatic, and isothermal. We have heat of solution calorimeter also, but that involves usage of acids, which is not good for a workplace. So it is right now obsolete. But still, there are three different types of calorimeters which we discuss now. In adiabatic calorimeter, this relies on a principle that at any point of time during the test, the temperature of the sample should be equal to the temperature of concrete. So if you keep the sample over here and if you keep on measuring the temperature and this is your surrounding, so the temperature of the surrounding should be equal to your temperature of concrete. Means if the concrete is at 20, you'll ensure that the surrounding is also at 20. If the concrete reaches 30, you'll ensure that the surrounding is at 30. Similarly, if the concrete keeps on reaching the higher temperatures, you'll see what is the rate at which the surrounding temperature should be increased. So this condition would require an additional heat to be supplied to the surrounding environment from outside. This is one thing. And it is considered adiabatic only if the temperature, we are maintaining the temperature of surrounding and the temperature of sample constant so as to ensure that there is a minimal temperature loss from the sample to the surrounding. So we say a system is adiabatic only if the temperature loss is not greater than 0.02 Kelvin per hour. Now, if we see this system, what is really happening in this system? Since we are increasing since the sample temperature is increasing, we are also increasing the temperature of surrounding. Now, since the temperature of surrounding is increased, the rate of reaction or the reaction kinetics of the sample, which is at higher temperature, would increase further. So we are not understanding what is the reaction rate of sample at a constant temperature. We are the temperature of the sample is increasing, because of which the temperature of surrounding is increased. Because of increase in temperatures of the surrounding, the sample reactivity will increase, and that would increase the temperature of sample further. So because of this, we are not again measuring the actual scenario. We can also have semi-adiabatic calorimetry. In this, what we do is we'll try to allow some amount of heat losses. So instead of increasing the surrounding temperature and all, we try to insulate the system. And in an insulated environment, how the sample temperature would increase. That is what we'll try to measure. So with an increase in time, how is the sample temperature is increasing. The heat loss is then again measured by keeping the same system and then understanding what is the heat flow from the sensors. Through this system, we can really measure the heat or the temperature of a sample, which is of relatively higher size. So we can use concretes with an aggregate approximately 16 mm. And to have a better signal to noise ratio, we can remove coarse aggregates. Still, we are actually measuring what is the reaction kinetics of the concrete through the hydration rate of cement. So the other materials are kind of inert material. So you can see your aggregates for better signal to noise ratio and then understand what is the temperature increase of your sample. And in semi-adiabatic calorimeters, we can, as I said earlier, we can really use larger samples, and the output over here is temperature with respect to time as shown in this schematic. Now comes isothermal. In adiabatic, what we have done, we have increased the temperature of surrounding similar to temperature of sample so that there is no heat loss. In semi-adiabatic, now instead of increasing the temperature of surrounding, we are insulating it. We are trying to minimize the heat loss from the sample outside, but we are not increasing the surrounding temperature. But whatever minor heat loss can happen are accounted. In isothermal, we are trying to maintain the sample temperature at a constant temperature. That is why it is called isothermal. Iso is constant, thermal is temperature. At a constant temperature, we would like to maintain the sample. This means like as sample reacts, there will be some amount of heat generated from the sample, and that generated heat would increase the temperature of the sample. Now, if I keep on removing the heat from the sample, then only I can maintain the temperature of sample at a constant temperature. which is called as isothermal condition. So we continuously remove the heat from the sample through this particular system, which is a heat sink. The same is the case for the reference. Reference is a non-reactive material and sample is a reactive material. Now then we'll measure from this heat sink. Heat sink would generate voltage. That voltage should be converted to power, and that power would be converted to heat. This is what we do in isothermal calorimetry. In isothermal calorimetry, as I said earlier, we measure the heat flow from the heat flow sensor as heat is conducted to the heat sink from the sample, and the output is the difference between the sample signal and the reference signal. This is to eliminate any crosstalks or any noise that can arise during the surrounding environment. And reference sample is important over here. As I said earlier, the sample will emit heat, and that would be gone to heat sink. Reference should be inert. Now, how much amount of inert sample should I keep? That is the question over here. So the heat capacity of the reference and the heat capacity of sample should be maintained together or should be equivalent to together. Based on that, we will now calculate how much amount of reference should go into the reference sample. So since we are taking out the heat from the sample, we would like to have our sample quantity as small as possible. So in isothermal calorimeter, we maximum use from 1 gram to 100 grams, depending on the type of calorimeter that you have in your laboratory again. So since it is very small samples, we usually confine our systems to paste systems. As discussed earlier, we are trying to maintain the reference sample in such a way that the amount of reference sample should have equivalent heat capacity, something similar to heat capacity of your sample. We'll try to see an example or try to understand better through this example. Say, for example, if you have 10 grams of OPC paste, which is made with a water to binder ratio of 0.4. Now we would like to understand how much amount of inert material. Inert material can be either water or quartz or any other material that I have to require to be loaded in the reference sample side. For this, what we do is we need to understand what is the specific heat capacity of this. What is the heat capacity of this total 10 gram of OPC. Now we have to add such an amount of water in the reference sample so that these heat capacities would match. Now to get the heat capacity of 10 gram of OPC paste of water to binder ratio 0.4, I need to know how much amount of OPC is present and how much amount of water is present. Once we get that, so that is a normal calculation. The amount of cement that is present in 10 gram of OPC paste is around 7.143 with water to binder ratio 0.4, and the amount of water we can see as 2.857. Now OPC has different specific heat capacity and water has different specific heat capacity. The specific heat capacity of OPC is 0.75 joule per gram Kelvin and water is 4.18 joule per gram Kelvin. Once we know these values are kind of material specific values. And once we know this, from the amount of sample that is present, we can totally calculate what is the total heat capacity of the paste sample that has been loaded in the sample ampere. That turns out to be 17.299 joule per Kelvin. Now we have to have water with equivalent heat capacity. Since we know what is the specific heat capacity of water, if we divide this one with the specific heat capacity, we can get to know what is the amount of water that needs to be loaded in the reference side. So through this calculation, we understood that the amount of water that required to be filled in the reference side is 4.138 grams. This would be sufficient to have an equivalent heat capacity of the 10 grams of OPC paste with water to binder ratio of 0.4. As I said earlier, it need not be a water as an inert material. You can also prefer quartz as an inert material. But quartz will have a different specific heat capacity, which should be accounted over there. Now, if you see the calorimeter curves that are obtained from between different calorimeters that we have discussed, and with respect to different variable that we are interested in, with respect to time and temperature, if you see, in isothermal, we try to maintain the temperature at a constant level, right? That's why it is constant over here. In adiabatic, the temperature keeps on increasing because as the temperature of sample is increasing, we are also increasing the temperature of surrounding. So the temperature would keep on increasing. And in semi-adiabatic, it is an insulated system. It is bound to have some amount of heat losses. So as the temperature increases to a certain extent, there will be heat loss. And the amount of heat loss that happens when the temperature of sample is at lower temperatures would be less when compared to the temperature of sample at higher temperatures. So you will end up having this particular curve. If you see the equivalent thermal powers, the thermal powers will also change like this. With higher temperatures, you'll have higher thermal powers. And if you convert this thermal power to heat or cumulative heat, you can see this variation between different calorimeter results. What does this tell us? This says that if you take a same sample and do measure the amount of heat or do a calorimeter test across 3 different calorimeters, you'll end up having different values. So even in this case, if you would like to understand or distinguish between different systems, it is always preferred to differentiate between the systems which are performed on same calorimeter. You cannot have a system curve with one with isothermal and another with adiabatic, and now you cannot try to understand or match or compare between these two heat flow curves. Coming to the calibration, it is important for us to understand what is calibration, how do we do that. And here we confine our discussion to isothermal calorimeter only. Since we are trying to maintain the temperature of the system at a constant level, a high precision thermostat is always required. And it is also good to maintain the temperature of the room at a constant level so that your thermostat load on the thermostat would be minimized. And there are certain calibration coefficients. The calibration coefficient which will help us to transform the voltage that is obtained from your heat sink to the equivalent thermal power, which is often called or often given in terms of epsilon, and it is measured by electrical calibrations, and this calibration should be done on a regular basis. A baseline should also be taken, and this baseline should be taken when you are changing your ampule. Say if you are having another system in the ampule. Ampule is the crucible in the teacher that we have discussed where we place our sample. Here we load it in ampules. Ampules are kind of vessels in which we load our sample, and then we will keep that sample in the calorimeter. So if we have any variation in this ampule, it is always preferred to have a baseline correction. So baseline is the signal of the calorimeter when no heat is produced in the sample, and you'll get a baseline voltage which is U0, and you'll always get the voltage from your sample. If we deduct the baseline voltage from your voltage, you'll have the corrected voltage from your sample, and that multiplied with the calibration coefficient that you get from the first step will give you thermal power. If you divide this thermal power with the mass of your sample, then you can get specific thermal power. So this units are in terms of watt per gram now. And another calibration is there with respect to time constant. This may not be of much significance if you are trying to understand what is the heat of hydration across a longer duration. But if you would like to understand what is happening really in the system at early stages, there you would like to have the time constant also. Time constant actually tells us, indicates the measure of thermal inertia of sample that blurs the details of rapid events. See, your sample is rapidly emitting heat or giving heat, and that should be taken by heat sink. Now there will be a temperature difference of the heat sink, and there will be thermal inertia of this sample, because of which you cannot accurately understand what is happening at next moment or at next moment, that time constant. So it talks more about thermal inertia. So it is used, as I said earlier, it is used to correct the rapid processes only because of time lag of an instrument. This is corrected in this form. PC is the corrected thermal power. P is the thermal power which we get from after baseline correction. This one that we are talking. Plus tau times, tau is the time constant. This is given by a person called Tian. So this equation is also called as a Tian equation. Time constant times the change of thermal power with respect to time. That is what we do. Now, what is this time constant? Time constant is cumulative of heat capacity on sample side by heat flow sensor to the apparent thermal conductance of the heat flow sensor. Once we know these two, we'll get to know what is the time constant. Once we know time constant, we can correct the obtained thermal power for thermal inertia of the sample. This is regarding the calibration with respect to time constants. So reference is always important. Reference would reduce the noise and drift in the measurements. And if you see the isothermal calorimeter, there are different types of vendors which will provide you with isothermal calorimeters. You have TAMAIR, you have several other vendors. Here I'm showing a picture of TAMAIR isothermal calorimeter from IIT Bombay, where I have done my PhD. If we desiccate this, we can see that there are how many caps? 4 caps in one column, and you have 4 such columns. You have 16 caps over here. 16 caps would refer to 8 channels. Channel here, I mean both sample ampule and as well as reference ampule. Both these two would correspond to one channel. So that is what is shown over here also if you totally. So this is one ampule. You have one sample ampule and the reference ampule to a heat sink over here. You have this 8 channel calorimeter block. You have the outer cover is aluminum support plate and an insulated cabinet would be there. Towards the end, you have Peltier temperature control module through which you can maintain your entire system at a constant temperature. You can always remove the excess heat through fan, and you have a data logger which will collect the heat from the heat sink, convert that to power, voltage, and obtain voltage to power, and from power we can convert to heat. This is the same thing that we have seen in the earlier slide, but with a zoomed fashion. And where do we find the application in cementitious systems? In cementitious systems, we can understand what is happening within the system with respect to time. That is what we try to understand over here. This is classic curve of isothermal calorimeter or heat of hydration curve of OPC hydration. If we see this curve, we have different information that we can try to obtain from this curve, right? Initially, what is happening? Immediately, there is an increase in heat flow rate. Then again, there is a reduction in heat flow rate. Now there is a constant heat flow rate for certain duration. After some time, again, there is an increase in heat flow rate. Then again, there is a small bump over here. Then there is a decrease in heat flow rate. And then there is a constant or a slow decrease in heat flow rate. The decrease in heat flow rate doesn't mean that the reaction has stopped. Now the reaction of the sample is happening at a slower rate. Over here, a higher increase in heat flow rate says that the sample has been reacted at a higher rate. So initially, when you have OPC with water, the surface of OPC will get wet. So this is also called as wetting or wetting of the surface, due to which there is a rapid increase in your heat. That is why there is an increase, and this increase also corresponds to dissolution of different ions from your anhydrated phases, which is a raw OPC that we are talking. After some time, there is a deceleration, means the rate at which the dissolution is happening has been decreased. It doesn't mean that the sample is not reacting. The sample is reacting, but at a lower rate. And then we enter an induction period where the rate again has been decreased significantly. And then due to some mechanism, there is a kick start of your reactions again. Means there is also a reaction that is happening, but the rate at which the reactions are happening has been increased over here. This phase, the third stage, is called acceleration period, where most of your silicates will hydrate. And then you enter a deceleration period. Again, I reiterate that the reactions are happening, but the rate at which these reactions are happening are at a lower level. This small bump over here tells us the sulfate depletion peak. And then there is a slow reduction in your reactivity, or low activity of your entire system is taking place over here. Now, where all we can see the applications, we can understand how the rate of reaction would vary with increase or decrease in your water to cementitious system or water to cementitious ratio. This is the similar curve that we are trying to see again. If you have a curve of like water to cement ratio of 0.35, 0.4, 0.45, and 0.5, what we can see over here, the time of appearance of peak has been shifted to higher durations. Similarly, if you accumulate this or if you integrate this, then you'll get a cumulative heat. If we see the cumulative heat, although we can see that the rate of reaction is higher in 0.35 water to binder ratio, the total cumulative heat of 0.35 water to binder ratio is lower when compared to 0.5 water to binder ratio. Here the space is more, means the amount of hydration that had taken place is higher over here when compared to this one. Over here, since the um, sample has immediately got some water, there is significant release of alkalis at the initial stages. That's why there is an increase in reaction rate. If you see what is the effect of, like, this study can also be, this analytical technique can also be used to understand what is the reactivity of different supplementary cementitious materials, or to understand how the addition of supplementary cementitious material would change the rate of reaction of your actual control system. So here there is a system with Portland cement. There is some amount of Portland cement replaced with quartz, some amount replaced with fly ash, and some amount replaced with slag. It is surprising that even if we add quartz, quartz is an inert material. We believe that inert materials won't react. But if we see the cumulative heat is higher, means the total reaction of the system, or we imply that the total reaction of the system is higher. Why is that happening? Because this quartz is now providing it is providing the filler effect. Means on the surface of the quartz, now there are several nucleation sites that are forming, which is increasing the total hydration of Portland cement. If we see with fly ash and slag, we can see that there will be pozzolanic reactions that are also contributing, and that would increase the total reaction of your Portland cement, or this is called blended Portland cement. All these blended Portland cement systems will also have increased heat release. This is with alkylated material. We have two different types of similar material, but we have added retarder to the system. And then we understood that in the normal material, we have a significant heat release in the initial durations. This is the reason why the alkylated materials would not provide prolonged workable times. But if you add some amount of retarder, you can significantly reduce the rate at which these reactions are happening. This can be seen over here. And here we can see, although the rate of reaction has been decreased, the total heat flow is increased, even with the addition of retarder. This says that, again, your total compressive strength can increase. In the TGA curves also, we have seen there is an increase in weight loss. Here we have seen there is an increase in heat flow. These two are now confirming the hypothesis that although the retarder has been added, the total hydration has been, or amount of hydration has been increased with the addition of retarder. Now I would like to take the raw data and show how to get from raw data to this point where we can plot both heat flow and cumulative heat flow curves. Before going to that, I would like to understand if anyone has any doubts, or we can take up that hands-on. Okay, it seems that no one has any doubts. This is one data that, yes, please.
Madam?
Anyone has?
Yeah.
Yes, please.
Good morning, madam.
Yes, good morning.
While we are inserting that cementitious material with water, we will mix and we will insert into the vial.
Yeah. So it depends on the type of vial we have. If we we should be very particular in these things. If we are doing external mixing, means if we are mixing the sample outside and then we are loading into the ampule, which type of calorimeter do you have?
Isothermal only asking, madam.
Okay.
Isothermal
So we can,
only. Mixing energy will affects the heat of vibration.
yes. The
mixing.
amount of mixing energy would affect, and the time after mixing that you are loading into the calorimeter. So like if you mix now and after 10 minutes, if you are loading into the calorimeter, that would also affect. Even if you mix immediately and then load into the calorimeter, and then you are mixing another sample and then trying to open the calorimeter lid and trying to load another ampule now, that would also affect the heat flow from the first ampule. So there are
Then we have
several
to
factors that
insert.
would affect. Sorry.
Ma'am, then we have to insert in the sample and then we have to mix in that incubate.
So few
Incubation
isothermal calorimeters would come up with this mixing unit. So in the vial itself, you can have a mixing motor, small motor. You can load your dry sample in the ampule, keep that dry sample in the ampule, keep that sample with the ampule into the calorimeter. This would be fitted with some arrangement with small motor and a syringe. After some time, you can push water through this syringe and start running your motor. That motor would mix the sample within the ampule itself. Means from the moment you have your contact of water with your dry sample, you are measuring your heat flow from the sample in that case. This is called internal mixing, or else we can do an external mixing, which is commonly used. In that case, we have to eliminate the initial 20 minutes data, at least 20 to 30 minutes data. So if you are more interested in understanding the early hydration reactions, then it is preferred to have internal mixing. If you are trying to see what is the total hydration, in that case, you can prefer for the later one.
Thank you.
Thank you. Any other doubts anyone has? Okay, now I would like to show what data we get, how to process the data, and how to come to heat flow curves and total heat flow curves or cumulative heat curves. So this is one data that we have generated from isothermal calorimeter. The data here we mean will have time, voltage, power, and heat. If I take these three values, now this is time, which is in seconds. This is this is voltage. I believe, yes. Voltage, power, and heat. Voltage in volts, power in watts, and heat in joules. Now, if you see, till certain time, you have disturbance in your isothermal calorimeter, and you have negative values for your power. We need to eliminate that data till where your negative values for the power is there. Now you can consider data from this time duration. Say from 1490, you have a power value of this much. Now this power is in terms of watt, right? Now we need specific power. Specific power will get once we subtract this with the amount of solids that are in the system. That we have noted earlier. That is like that you'll record the weight of the sample while you are performing your experiment, and that will be given in your report also. So here the cement mass is somewhere near to 52.57. We'll take that 52.57 and then we'll divide. So if we do this, we have now watt per gram. Now we would like to convert watt per gram to joules. So now the watt will be converted to joule per second. Here we have considered the interval as 2 seconds. The first data is at 1490 seconds. The second data is at 1492 seconds. The previous data is at 1482 seconds. So you'll multiply with that time interval. Now that time interval is not constant. After 1 hour, we have shifted the time interval to every 1 minute. So till 3600, I'll drag this data. And at 3600, I'll convert that to 60. So till where we have, till here we have 2 seconds interval. From there, I have 60 seconds interval. So for this data, I'll take the same formula, but instead of multiplying with seconds as 2, I'll multiply this with 60 now, because the interval is 60. Now that is kept constant till the end of your experiment. This would give the value of joule per grams. Now we would like to have the total cumulative value from this. For cumulative, we'll go to the first slide, first cell. So for cumulative heat, we'll take this, and for the second one, we'll add this and the, So we'll consider the heat at this particular time interval, and we'll sum up with the previous heat. Like that, we'll end up having the cumulative heat. Now you have heat flow and cumulative heat that you can take to your origin. and then consider the equivalent time. Okay, so you have this as time. Sorry, this is heat flow rate, and this is your cumulative heat flow, which are normalized with respect to 1 gram of your sample because we have divided with the sample. Now you can draw these two in the double axis. So this is what this is what we have seen in this curve as well. So if you take this black curve, and this is one and the same, which are talking about heat flow rate in the system. And if I accumulate that with respect to time, this is what will give us the cumulative heat flow from that particular system. And how this cumulative heat flow and how the heat flow rate are changing by changing the systems or with respect to curing age or hydration age can also be studied. And if you can also correlate the total amount of heat flow to the compressive strength, this may not go well hand in hand for all the systems, but you can also understand about it. And if you try to increase or study the same thing at different temperatures, so this is a thermostated temperature, right? Like isothermal, right? You can maintain the temperature of thermostat at 25, at 30, at 35, at 40. You can increase the temperature of your thermostated environment, and then you can study how the kinetics of the system would change with increase in your temperature. That would give you the activation energy of the system. And that can be used further for your thermodynamic analysis or any other processes. Is that clear? So that would sum up isothermal calorimeter part. Maybe we can, like, if we have any doubts, we can take that one now. Any doubts anyone has? It's always good, like if we don't do this processing, usually the system would give us whatever calculations we have done over here. It might have considered from the initial point where the negative power is also coming. So this joule is converted from this one and cumulated from that. So you'll have that effect, which is carry forward. And you can also eliminate the initial 20 minutes data, and then you can start processing your data in this way, and then plotting and understanding what is happening in your the system with respect to time. That you can understand. Okay, so isothermal calorimeter will tell us it won't tell us what type of reactions are happening. It will only tell us whether some reaction is happening or not, and at what rate it is happening. Okay, it may not give us an idea like what type of hydration product is formed. I hope it is clear. If you have any doubts, we can take it up now.
Hello, ma'am.
Yes, please.
Can we estimate the initial setting time from this data house?
Can we estimate? Yeah, there are some studies which talks like the end of dormant period can be, or induction period can be correlated with the initial setting time. But again, if your system varies, then we need to check whether we can really correlate this or not, because we are just measuring the heat. We are not understanding. But heat is also measured or evolved because of some reaction that is happening. And because of that reaction, your plasticity of the system would go down. And if there is a reduction in the plasticity, then the setting time would happen. That is what is governing. So these are all interrelated. But we cannot directly say that for every system, it is at this point on the curve, the initial setting time will happen. But you can still have correlations among different test methods.
And